Hi guys, this is Anno from the Xzistor lab, and in this demo video we are back with Troopy, our little Lego robot, and we're going to see how fatigue works in the mind. So we're going to chase Troopy around a little bit and see what happens when he gets exhausted. We will first look at the fundamentals of fatigue, then how fatigue works in humans, and then we'll also see how we can model fatigue in robots using the Xzistor concept brain model. And finally, we'll take a little look at the dashboard when the model is running, just to see what happens inside the brain when the robot experiences fatigue. So what is fatigue? I think we all know what fatigue is. We all get exhausted when we do exercise or run around. Normally we get out of breath and our muscles start to ache. And that's, like I said, it's caused by running fast, if we climb uphill or carry heavy objects. We are not talking here about general weariness or sleepiness. We're specifically talking about physical exertion here. So when we look at robots, most robots do not have muscles. They actually have motors. And the question now is, of course, can robots feel fatigue? So we say yes, we can create the same sensations that humans experience when they feel fatigue in the robot brain. Depending how hard the robot motors work, we can create the same negative sensations using the Xzistor concept brain model. We can even create the equivalent of muscle pains. This is a bit of a busy slide, but we see at the top here this little character pushing the 10 pounds along. And if we look on the right hand side, the curve that shows his effort level, it's the pink curve, never really exceeds the fatigue limit. So theoretically we say this 10-pound weight he can push along indefinitely, and he will never get tired. If we come down here now, we increase the weight to 100 pounds, and this we can compare to, let's say, pushing a car along the road or a particularly heavy wheelbarrow. And if we look at the curve on the right hand side now, we see the pink curve, the effort level has shot up way past the fatigue limit. And now he will start to eat into his fatigue reserve, or his energy reserve that he has got due to the exertion. And this will carry on up to a point where he gets too tired or fatigued, and his muscles will be prohibited by the brain, and he'll start to feel muscle aches and pains and feel very tired. That will force him to stop the activity, and immediately the effort level will drop right down, and he'll be able to recuperate or rest down here. And that's the effect of this fatigue limit. Once the effort exceeds the fatigue limit, we're into a sort of a time-based scenario where a limited amount of energy will be available, and it's presented by this area under the curve. And once the steeper the pink curve is, the quicker he'll sort of use up the reserve energy before he gets tired. And that's the simple sort of fundamentals we can use when we model fatigue in the robot brain as well. So let's just take a look again. Now we say he's pushing the 100 pounds along. We have the effort level, the exertion level there. We see the rest as we have discussed. Now if we come down here and we look at the exhaustion level, so this is actually how the human mind will subjectively experience fatigue or just exhaustion. So as we start to exceed the fatigue limit, we will see that we slowly start to become aware of a feeling of tiredness. And we can just imagine if we push a heavy wheelbarrow along and we just get to a point where we say, okay, now I'm running out of energy, I'm starting to feel tired. And as we go up this curve at the bottom here, we see the increasing feeling of exhaustion shoots up, and it comes to a point where we say, okay, this is enough, stop the activity. At the top here, we see the pink curve will drop down, there's no more effort, and we will see the feeling of tiredness and exhaustion will start to decline slowly as we rest and we recuperate. And that's just an important principle, because this is the same kind of subjective state we want to generate within the robot. With this red arrow here on the top graph, this is the point where the peak fatigue kicks in. And on the left hand side we see here that the three main states that are being generated is a feeling of tiredness, which is an unpleasant state. The muscles will be restrained from moving, and we'll also feel pain, which will also be an unpleasant state. And these unpleasant states we can obviously model with the Xzistor concept brain model. If we now look at the how fatigue works in the human brain, the brain triggers a reduction in muscle performance to avoid physiological limits from being exceeded. And we'll see that the muscle nerve impulses actually inhibit the motoric area in the brain, very much similar to pain. So a lot of the fatigue sensation or subjective state it happens in the brain rather than in the muscular area. Some of the other chemicals making muscles work include adenosine triphosphate, glycogen, and creatine phosphate. It's also interesting to look at the role that calcium plays in activating the muscles. So one can go and read a little bit more about that to understand better how it works in the human body. When we move on to the robot, obviously we now need to move from the muscles to the robot motors, because most robots at the moment are using motors. Although there is some interesting muscle designs going on, there's some progress in that field, but we'll work with motors for this presentation. And now if we look with electric motors, we see it can do exactly what the human can do in terms of the human effort. So where we calculated the human power or the effort level using force multiplied by speed, it's very handy that for the electric motor we can do exactly the same. So we can calculate the power by multiplying the torque with the rotational speed. Also, from an electrical point of view, we can just multiply the potential difference with a current, so V times I, the very common equation, and that will give us the power of the motor. So we have got a way to measure the effort level, and there's some induction losses and some friction losses involved there, but pretty much a simple way to calculate the power in an electric motor. So if we see the electric motor exerting some effort there, let's look at the power level down here. So we see exactly the same as our fundamental discussion we had. We have the power level. For a typical electrical motor, you'll have a nominal power. Any kind of effort below the nominal power will almost be able to continue indefinitely. But the moment you shoot over that nominal power, you're into a sort of a area where the motor starts overheating, and we need to slow the motor down. So depending on the level of effort here, the motor will have to be slowed down, because the heating will actually destroy the insulation on the windings and other damage. So exactly like with the human fatigue, where we want to prevent damage to the muscles, in this case we want to avoid the damage to the electric motor, and we give it a finite bit of energy that it can expend in this regime before we want to kick in with pain and tiredness and restrain the motor movement in order to give it a chance to recuperate and cool down, so we can get back to below the nominal power. It's interesting that if we look at this, the heating effect here, this could be a very interesting derivative state that we use. So in some cases we can use the power level to generate these subjective states in the robot brain. A good derivative would be to use the heating, so we can easily stick a thermocouple in the motor and just use the heat to decide when it's time to kick in with a fatigue effort to slow the motor down. So that's one simple way we can build that into a robot. The Xzistor concept brain model can generate the following in the brain of a robot. So we are able to generate fatigue, that tired feeling, unpleasant feeling. We can restrict the movement of the motors, and we can also create pain. So we can even create the pain in the areas of the motors, individual motors. The brain model can use existing algorithms and use readings of parameters like motor power level. We can use the motor current, we can use the motor torque, motor speed, and like I said, as a derivative, we can also use motor temperature to generate fatigue in the robot brain using the existing algorithms. So no specific new algorithms are required. We can use exactly the basic building blocks we have in the model as is. So let's turn to Troopy now, our little Lego robot running the Legos replacement firmware. And let's take a look at Troopy dragging some items around his confine, and we'll see how he gets exhausted. This little car Troopy can probably pull around indefinitely without getting tired. Pulling around Black Bear is putting more strain on the motors. Just to say no animals were injured during the filming of this scene. Now let's take a look at the flashlight, which is becoming more hard work. This loading will tire Troopy quickly, but let's see what happens when he gets chased around his confine by two Thai ladies on horseback. This is all about motor speed.
สวัสดีค่ะ สวัสดีค่ะ Yikes สวัสดีค่ะ สวัสดีค่ะ แล้วก่อนมิสเตอร์โรบอท แล้วก่อนมิสเตอร์โรบอท
Let's watch Troopy work out with his personal trainer. So after looking at Troopy experiencing some exhausting activities, let's get back to modeling fatigue in the robot brain. My initial consideration was to actually put a incline in the learning confine, so something like a mountain. And the initial idea was to have the robot experience fatigue and then learn to avoid the steeper areas in the learning confine. There was some difficulty with that in the sense that it was physically probably difficult to construct in the learning confine, and then also I was worried about the Troopy just keeling over and getting damaged. So I stumbled onto another idea which simplified things significantly, and that was the idea of actually using like a sticky pad, or if a mud patch, if you like, in the learning confine. Which will increase the strain on his wheels. So it's literally like he gets onto the sticky pad or this mud patch, and suddenly his wheels are constrained. It's much more effort for him to move. And that was a simple way to achieve exactly the same as a steep incline or a mountain or a relief. But we could do it on a flat surface and then save the robot from being at risk of falling over or getting damaged. So here we see the learning confine, the floor of the learning confine, and we see the brown area there on the left-hand side is the mud patch. Let's just take a look in real life what it looks like in the learning confine. This is a top view of the mud patch, showing us where it is located on the floor of the learning confine, and we'll just take a little peek over Troopy's shoulder. To see where it's positioned, and we see we've even got some warning signs there to warn Troopy of the vicinity of the mud patch. And before we take a look at how he encounters the mud patch, we'll just take a moment to discuss the concept of a virtual tutor, which is important to understand. When Troopy registers the color brown on either his front or rear color sensor, he'll know he has entered the mud patch, and he'll immediately feel much more strain on his wheels, and his speed will be greatly reduced. He will feel fatigue, an unpleasant feeling, and mild pain, either in the front body area or the rear body area, depending on which sensor registers the color brown. And we can even go later on into more detail and actually locate the pain exactly on the motor that is experiencing the strain. But at this stage, for this technology demonstrator, we've kept it simple, and pain is only experienced in terms of the body map in the brain, either the front body area or the rear body area. Like with humans, most fatigue functionality is built into the brain and not the motors. So much of the regulation is happening in the brain. The motors might still be fine to go for quite a while, but the brain is making the decision as to how the subjective feeling is passed on and presented. So we will make Troopy feel tired and unable to move faster without putting actual strain on the motors. So like we said, Troopy will find the sensation unpleasant and he will learn to stay away out of the mud patch. And that'll happen over some time, of course. At first, Troopy will need to be shown how to get out of the mud patch. And for this, we are going to use a virtual tutor. And what this is a simple routine written into the software of his brain that senses he has entered the mud patch, and then it'll help him out. So let's say the front sensor reads brown, then the virtual tutor will reverse him back out of the mud patch. If the rear color sensor reads brown, the virtual tutor will actually move him forward so that he can get out of the mud patch. And that is just a simple arrangement I built into the brain model because I didn't want to take the time to, every time he gets into the mud patch, to move him out of the mud patch. So that's quite an elegant solution. It's something to think about in future Xzistor concept robots, where you actually can have a pretty dumbed down or even a kind of a mindless virtual tutor which teaches the robot some very complicated behaviors, whilst actually in itself not understanding what the purpose is. It's got no awareness. It's just a software routine. What the benefit of that is, of course, is we don't need an actual tutor, and this can be switched off once Troopy has learned to navigate out of the mud patch. So eventually, just looking at the mud patch will actually generate bad emotions in Troopy. So literally just walking past that area, he will develop bad emotions and sort of steer away from it, unless really urged for some other reason to move closer to the mud patch. We'll now take a look at physically when Troopy gets stuck in the mud, and then afterwards we will just look at when we run the Xzistor concept brain model on the computer, just interpret the graphs on the dashboard. So here we have Troopy in his confine, and this is his first encounter with the mud patch in his confine, and as you can see, he's turned it into a bit of an adventure. He's got his adventure map there. He's got his walking stick just in case he encounters any snakes or anacondas, and of course, like any self-respecting adventurer, he's got his mobile phone ready just in case he needs to phone 911. And nobody actually knows why this place is called the Green Piranha Swamp. Let's take a look what happens when I steer Troopy onto the mud patch for the first time. I'm just starting up the Xzistor concept brain model program on the laptop, and the program is running. I can see the dashboard and the video is on, so I can take charge of the robot now, and I'm going to drive him onto the mud patch, and then we'll just I'm going to hand over to the virtual tutor there. The moment he's on there we go, and now you see the wobbly motion is the virtual tutor trying to bring him out of the mud patch, and his wheels are constrained. He's feeling fatigue and pain, and he's coming out of the mud patch now. So hopefully he's going to learn from that, and then slowly in time he will learn to avoid the mud patch and stay away from the mud patch. All right, well done, Troopy. Here we have Troopy approaching the mud patch. I'm just going to take control of Troopy, and we'll drive him a little bit closer. As we can see, we are there in the area of the mud patch. There's the warning. I'm now turning him towards the mud patch, and I just want to show at this stage, if you look at the graph on the right at the top here, just keep an eye on that graph. I'll point out the moment he moves onto the mud patch, we'll see a brown line appearing there, which will show the pain level, the muscle pain that he effectively will feel on the front of his body. I'm now going to drive him straight into the mud patch. And there we go, he's on the mud patch. If we look at this right hand graph, we saw the brown line has appeared there. It's what I would term as a medium pain. So he's experiencing medium pain. If we come over to the left, we can see it's a negative state of mind that he's experiencing. We look at the facial expression down here. See, he's not too happy about the state of affairs. And then if we come to the right here, the general happiness curve, we see the blue line is well below the yellow line. And what I'm going to do now is I'm going to just release control of the robot, and the virtual tutor will kick in and bring Troopy out of the mud patch. But we will see, it might not be this obvious, and there I go. Right, so he's moving very slowly. The virtual tutor is bringing him out of the mud patch. It's hardly, you can hardly see it on the video, but he is moving backwards out of the mud patch. We'll keep an eye on this right hand curve, on the brown curve. The moment he's out, there we go, he's outside the brown mud patch, and suddenly I'm just going to halt him there. So suddenly we see that the brown curve has disappeared. He's not desperately unhappy anymore. He's starting to experience a little bit of hunger. But if I now let him do his thing, you can see he's in play mode again, and he's happy and he's smiling. And there he had a bit of a fright because he saw the black patch. Don't worry about that too much. Let me turn him back. I'm now going to drive him back into the mud patch again. Now remember, he's not had an opportunity to learn anything about the mud patch. So for him, it's basically a brand new experience. He's hardly learned, that it's painful and it's strenuous, and he wants to get out of there. So I'm driving him back on there now, and we see the brown line reappearing there. Again, unhappy, and facial expression unhappy. And on the right hand side here, we see the general happiness curve. The blue line is below the yellow line. Just to, if we look at this brown line over here, we see the level what we would call medium pain. So it's not an intense pain, it's a medium pain in the front of the body associated with the strain that is experiencing, the muscular pain in effect. I'm now just going to move him forward so that he actually crashes into the wall, and then we can see the difference in the pain level that he'll experience. So I'm just going to take charge of him now and drive him forward carefully into the wall. So just keep an eye on this right hand top curve here where we see the brown line, and we'll just see what happens when he moves right into the wall. Now moving him forward, and there we go. So we see way much more pain, and there's the fear that's associated with a crash into the wall. Much more than the pain just from the strain and the fatigue in the mud patch. If we come to the left here, we see severe negative emotion. We can see the face is in distress, and here on the right hand side in the general happiness curve, the blue line is so far down, it's actually off the curve. So let's alleviate Troopy's pain a little bit. I'm just going to let him do it himself. So there he's pulled out. If we come to the right hand curve here, we see the pain is gone, the fear is slowly diminishing. The brown curve is still there. The virtual tutor, there the fear goes, and now it's just the strain on the motors that's left. This brown curve in the mud patch as the virtual tutor is bringing him back, and there we go. He's out of the mud patch, and hopefully he'll learn something from that. Now for some final thoughts and conclusions. The Xzistor concept brain model allows robots to experience fatigue, pain, and a reduction of power to its motors. And these are not just parameters on a graph, these are actual subjective states experienced just like humans would. The robot will learn to avoid anything that causes strain or fatigue. And Xzistor robots will learn to optimize efforts and conserve energy. And one practical example one can just think of is, let's say we deploy a colony of Xzistor robots to another planet like Mars, for instance, and we will let them learn and evolve in that environment with specific missions. We can then allow these robots to learn to optimize their efforts, thereby saving their motors and not overextending themselves. One can even go further and say, let's build in a reflex which will allow extra power and less pain to the motors in case of an emergency. For instance, if the robots on Mars register a sandstorm, we might release extra energy and alleviate the fatigue feeling in the brain, almost like an adrenaline rush. Allow them extra energy to make a safe passage to a area of protection. So this all-comprehensive model opens up an amazing view on the future of aware humanoid robots. And that's sometimes why we say the Xzistor concept brain model allows us to see 1,000 years into the future. So in time, Troopy will learn that he does not need to climb the mountain, that he can hitch a ride with friends instead. And so to conclude this video, let's watch Troopy travel to the top of the mountain with some friends. Come with and enjoy the mountain vistas with us. This is Anno from the Xzistor Lab signing off. See you in the next video.
Afternoon, ladies. Are you ready for our trip up the mountain? Don't spare those horses, ladies.
And having suffered no fatigue on the way up, here we see Troopy with the two Thai girls arriving at the top of the mountain. Everybody is happy to see them.
Well done, Mr. Robot. Lolo.